welcome to this video about complex roots using de Moivre's theorem, as it's said at the top of the screen. So what is this all about? Well, what we're going to be having a look at here is trying to solve an equation which at face value looks like it's got a pretty obvious solution, which it does, but there are going to be, as we'll see, some other solutions. So let's say we want to solve z to the power of 3 equals 8. Well, I think we could probably say z equals 2 is the solution, because 2 to the power of 3, 2 times 2 times 2, yeah, that's 8. That's good, that's one solution. But are there some other solutions? Well, yes, there are. In fact, there is a theorem called the fundamental theorem of algebra, which says if you've got a polynomial, and here we do have a polynomial of degree 3. So what do I mean by degree 3? If it's z to the power of 3, this is the degree. If it's degree 3, that means there will be 3 solutions. And we'll see in a moment that's actually going to be true. There are 3 solutions to this equation here. Well, where are the other 2 solutions? Well, what we're going to do is we're going to write this 8 in polar form. Why? Just bear with me for a moment. If you think about 8 on an argand diagram, okay, let's try and represent a very simple argand diagram here. So let's draw a line. Okay, let's get some sort of colour that stands out. Get my keyboard handy so I can actually get some straight lines being drawn. Okay, let's draw that about there, and let's draw another one like that. Okay, so coming back to the pencil tool, this is the real axis, and this is my imaginary axis. Okay, let's say 8 was about there. So if I represent where 8 is on that argand diagram, well, I need to go from here out to there. So the modulus is 8. The angle, okay, the argument, the angle between this line and the real axis is obviously 0. So that would say that 8 is going to be 8 cis 0. Alright, seems all fair enough. Okay, so the distance is 8, the argument is 0. Alright, so well, what has that got to do with anything? Well, let's employ de Moivre's theorem to show how we can get one solution, that solution of 2, and then we'll come back to this stage here in a moment. So I'm going to call this solution Z1 because there are going to be some other solutions. Now if I want to get Z on its own, I can take the cube root of this side and the cube root of this side to keep it balanced. The cube root is the same as the power of a third. Okay, so let's just put that over here. I've got n, the cube root of n, that's the same as n to the power of 1/3. Okay, now if I then employ de Moivre's theorem, that would say take 8 to the power of a third, which is the cube root of 8, and be cis, we would multiply that power times the argument, which is going to be 0, and that would just give Z1 is equal to cube root of 8 being 2, cis 0, and the cosine of 0 plus I times the sine of 0, okay, that would be still 0. 0, so that's going to just give 2 as the answer. Alright, so that's a lot of work just to get the solution to 2 that we already knew was correct. What about these other solutions? Now, to say we're going to come back to this line of working here. Now, I think if you look at this Argand diagram again, okay, this well, distance out 8 here, okay, and the argument being 0, I think you probably would appreciate and accept that if we had the argument being all the way around there, which is 2 pi radians, that would also take us to exactly the same position on our Argand diagram. The modulus 8, the argument being 2 pi, would also take us back to here. Now, for those of you who are alert, you're probably thinking, well, that would be true if we went 4 pi radians around, or 6 pi radians around, or 8 pi radians around, or really any multiple of 2 pi, where, I know, let's just say k is equal to some sort of number like 1, 2, 3, 4, etc. So some multiple of 2 pi, and that set of numbers is called the, yes, you're absolutely right, you're all guessing it, telling me natural numbers. Okay, so let's get that second solution. So if we had z cubed equals to 8 cis 0 plus 2 pi, and we get that power of a third over to this side like we did before, all of that to the power of 1/3. Okay, let's call this solution z2. Okay, that would be 8 to the power of a third. We've seen before that's 2. And cis, we multiply that times that. Well, 2 pi plus 0 is just 2 pi. 2 pi times a third would be 2 pi over 3. Is that a different solution from this one? Yes, it is. And we can plot these solutions on an Argand diagram more carefully later. Definitely see that's true. This is an angle of 120 degrees if you think about it in degrees, so definitely different from this solution here. What about a third solution? So let's call this, say, z3. So let's just erase that 3 down the bottom there for a second. Let's actually start that little bit again. So z is equal to 8 z cubed, 8 cis 0 plus, let's use 4 pi this time. So z, let's call that the third solution, would be 8 cis 0 plus 4 pi, all to the power of a third. So z3, 8 to the power of a third, that's 2. 0 plus 4 pi is 4 pi. We're going to multiply that number times that argument using Moivre's theorem, and that would be 4 pi over 3. Now 4 pi over 3 is going to be 240 degrees. Yes, okay, that will be 240 degrees. So that is going to be a different solution from these other two. Now you may be wondering, hey, what about if we use 6 pi or 8 pi or 10 pi, are we going to get even more solutions? Well, what we're going to find is that these solutions, these three solutions, are going to start repeating. Okay, let me just demonstrate that with, say, 6 pi quickly. equals 8 cis 0 plus 6 pi. Same working, let's call this Z4. 8 cis 6 pi 0 plus 6 pi 6 pi, all to the power of 1/3. Okay, so Z4, that will be 2 cis, now 6 pi over 3, 6 divided by 3, that's going to be 2 pi. But 2 pi is just the same as going back around that full circle again, so that's really no different from 2 cis 0, and that's something we've already got over here, the solution. So that's just the same as Z1. So we haven't got another unique solution. Now if you repeat that working for say 8 pi and 10 pi, you'll get these solutions being repeated, and you can prove that for yourself. Okay, so what does this mean in general? Well, what it means in general, if I go to a new page here, if we had z to the power of n was equal to cis, and we had some argument and multiples of 2 pi, we could solve that using good old Moivre's theorem and moving that power to the other side. That will be power of 1 over n. So the different solutions we're going to get can all be obtained by employing de Moivre's theorem. So r to the power of 1 over n cis theta plus 2 pi k over n. That's a pi there, not an n. Okay, and if you let k be different numbers from, in fact, starting with, in fact, 0, 1, 2, 3, etc. So what I said before about these being natural numbers, not quite right, because 0 and these other numbers makes it into, yes, you're all telling me whole numbers. Okay, so this here is a way in which you can solve some sort of equation like this one here, okay, using this here. Alright, and we'll have a look at more examples of that in class tomorrow.